Alright, hey guys, it's Miss Summers with your notes today to help you prepare for your astronomy test. So this video is for academic Earth. Y'all have a sheet of paper. You can use this paper on your test. You can write as much or as little as you wish. You may use anything from the note or anything I'm about to say. I'm just going to spend a few minutes going over the most important topics for astronomy that you definitely want to know. So this is sort of your last ditch effort to study. Alright, so I'm going to go in order by how we did this unit. So the first thing that we talked about in the astronomy unit, we talked about models of the universe and how there are two kinds. There are actually multiple kinds, but these are the main two that people have sort of looked at through history. One is geocentric, and the other is heliocentric. So geocentric, you remember that geo, this word, means Earth. So in a geocentric model of the universe, the Earth, let me see if I can fit that. No, I can't. The Earth is in the middle, and things like the sun and other planets orbit around it. And the Earth stays still. Now, we know that that's not accurate. That's not right. The Earth does move. It moves around a heliocentric solar system. So helio, remember helio, means sun. The sun is in the middle. So here's my sun, and then planets and other things like Earth orbit around that. Now, the sun is not the center of the universe. It's the center of our solar system. The sun itself can actually move too. But those were our two main models. All right. Once we went over those models, we then started talking about how the universe got here. And that is Big Bang Theory. Now, Big Bang Theory, the key words you need to remember for Big Bang is origin of universe. And basically what it states is the universe is expanding. You see what I'm doing here? I'm spreading my letters out. The universe is getting bigger. So it started as like a little itty bitty dot, and then it got bigger, and it got bigger. And then it started to cool down, and that's how we made things like matter. Now, the evidence for Big Bang, because remember, a theory in science needs evidence, or has evidence. All right, the evidence for the Big Bang Theory is this thing called redshift. So the light from galaxies moving away is stretched. See what I'm doing with my word here? Towards the red end of the spectrum. So that is how we know that the universe is indeed expanding. All right, and that's all I really need you to know about Big Bang Theory. So let's just move right along, children. All right, after we talked about origins and models, we also talked about nebular theory, which all you need to know for that, friends, is that that's how stars and planets and galaxies form. Big Bang is how the universe was made, or how the universe started. Nebular is about planets and stars and galaxies. So after we talked about all this fun stuff, we started talking about how planets moved. And we talked about this fellow named Kepler. And I'm going to move that just a smidge so you can see. Remember, Kepler was a guy, he was studying how the shape of how planets orbits, and he went to that fancy island where they had really good measurements, and he was like, wait a minute, something doesn't look right here. See, a long time ago, people thought that planets moved in circles, and some of you may still believe that, or some of you may have had that notion when you came in. But Kepler soon found that that just wasn't true. So he had to come up with some laws to explain, or not explain, but describe the way that planets move. Laws are descriptions. Theories are explanations. All right, so the first law is the law of ellipses, which is an oval shape like this. So, orbits are ellipses. They are this shape. They're not circles. The sun is one of the foci of the ellipse. All right? Ellipses have, that says have, eccentricity. Oh no, I'm not going to space that out. That's okay. Ellipses have eccentricity. So a circle is low eccentricity. All right, it's all very even. Something like this has high eccentricity. And you can see in my little drawing how I make something have high eccentricity is by moving these foci apart. All right. Now, what's cool about the first law is it means a second law is necessary. The second law is the law of equal areas. So the law of equal areas, we talked about this with water. Give me 1 second. So if you have a tall, skinny container, there we go. Let's take a look here. If you have a tall, skinny container versus a short, fat container, all right, these two containers can hold the same amount of water, all right? It doesn't look like it because this one's a lot taller, but it's narrower, whereas this one's wider, all right? When planets orbit, as they get closer to their star, I see I have low battery, thank you. As they get closer to their star, they have to sweep out a greater distance to make the same area. These are the same. So you're faster at perihelion, which is this point. Remember, peri means closer. And you're slower at aphelion, which is over here. All right, that is the second law. The third law is the law of harmonies, or harmonic motion, or periods. It's all the same thing. But my favorite thing about this law is it's the most common sense. All right? The closer a planet is to the star, the faster its revolution. Remember, revolution is a fancy way to say a year. So if here's my sun, this planet will take the shortest amount of time. This planet will take a little bit longer. A planet way out here is going to be even longer. Okay? So I'll write that down here. Longer revolution. And those are Kepler's laws in a nutshell. All right? So we talked about Kepler's laws. We talked about the universe and then how planets moved. Now we want to talk about how Earth moves. And again, you can write as much or as little of this as you want. You don't have to write every single thing I'm writing unless you feel like you need it. So the two main motions both start with the letter R. We have rotation and revolution. So rotation, I'm going to draw a picture. is a spinning of Earth on its axis. One rotation is 24 hours. And because one rotation is 24 hours, rotation makes day and night. All right, like let's put the sun over here. It's going to be sunlight. It's going to be daytime on this side and nighttime on this side when you're facing away. A revolution all right, that's an N. So a revolution, the orbiting of the Earth around the sun and their respective barycenters. Remember, a barycenter is like a seesaw. It's just the point in between two masses. Because the sun's so big, the sun is like a really, really big kid on a seesaw, you have to put them really close to the barycenter in order to keep everything balanced. So those are our two main motions. Our minor motions, precession, which is changing which way the Earth is facing in space. So imagine a top going like this, going like this. It's a very slow motion. It takes about 26,000 years to do one precession. The other motion is nutation. So nutation happens while you're doing precession, but it's this wobbly motion. Nutation is the wobble. The wobble changes the tilt of Earth ever so slightly. And remember, when the tilt changes, seasons change. All right, tilt changes seasons. So write that down if you need to, and we'll carry on. So after we talked about how Earth moves through space, we talked more specifically about seasons. You do need to be okay with those season diagrams. Let me draw a quick run right here. We'll do it like this. All right, so we have the Earth as it's revolving around, and you see that the Earth is tilted at 23.5 degrees. All right, when you're tilted away, that means it is winter because you are receiving less direct sunlight. So if I take this, you see how this light is barely scraping by? This would be winter. When you're tilted towards, that means it's summertime. Because it's not that you're closer, it's like you're getting more direct sunlight. Like here. All right, and if we want to see what that looks like, actually no, we won't do that. This picture is good. All right, so when you look at this diagram, summer and winter are always going to be on the left or the right side. So that's summer, this is winter, and in between, well, after winter, this is not tilted away or towards, neither of these, it's like the same. So that's spring, which means this is fall. Now, remember, opposite hemispheres, because the Earth is a ball or a sphere, opposite hemispheres make opposite seasons. So when we're tilted away in the winter, our friends in the southern hemisphere are tilted towards, and it's summertime. When we're tilted towards the sun and it's summertime up here in the northern hemisphere, it's winter down here in the southern hemisphere. So like places in Australia, in the south, in the southern hemisphere, it gets cold in June and July, whereas here it gets warmer. Their hottest months of the year are December and January, when that's our coldest. It's because of how the Earth is tilted. Remember, more tilt will lead to more extreme seasons, which means logically, if there's less tilt, there's less seasonal changes. All right, so we talked about seasons. 2 more things to talk about. We have tides in the sun. So, tides, remember, are caused by gravitational pull from primarily the moon and to a certain extent the sun. The moon has a larger effect, not because it's bigger, but because it's closer. The sun is bigger, but it's way farther away. All right, so the sun will be at certain positions, and the moon and the earth will end up changing how they are to one another when they all line up. So here's the sun, here's the earth, here's the moon. When they're in a straight line, that is a spring tide. So, large differences between high and low tide. This will be during a full moon or a new moon, because the moon and the sun are sort of acting like they're on the same team in tug of war. They're pulling the water the same way. So the high tides get really big and the low tides get really low. The opposite of that is called a neap tide. Neap. That is when the sun, the earth, and the moon can be over here or it might be over here, but neap is at 90 degrees. This is the smallest difference. Because what's happening, the moon is trying to pull water this way, the sun is trying to pull it the other way. So it's like they're on opposite teams of tug of war. This is going to be during a quarter moon, when the moon looks like this. All right. And the last thing that you should know, the last topic we talked about 2 days ago was the sun. You did these notes by yourself. We went over the lab. The sun is important to us because it provides energy for life and it heats up the surface of Earth. So, let's talk about the energy, and we'll sort of follow its track from the sun to Earth and all that fun stuff. So, the sun makes energy through fusion. And fusion means atoms come together. 2 hydrogens, which are 2 small things, H and H, get forced together because the sun is so big, there's so much gravity. It forces them together, and these 2 little things are going to come together, and it's going to make a helium. So hydrogen turns into helium. This also makes a whole bunch of energy. This energy is in the form of light and heat and ultraviolet light. The energy radiates